Hello friends, welcome back to this online certification course on watershed hydrology. I am Rajendra Singh, professor in Department of Agriculture and Food Engineering at Indian Institute of Technology, Kharagpur. We are in module 2. This is lecture 1 of module 2 and the topic is hydrological abstraction. In this lecture, we will cover abstraction, we will define abstraction, we will talk about types of abstraction, we will then discuss interception, depression storage and evaporation. Let us start with defining abstraction. Abstraction literally means something pulled or something drawn away, that means something taken away from some system, and that simply means it is, in one sense, it is a loss to the system. So, that is what abstraction is, and basically it is the process or processes by which water is removed from the natural hydrological cycle or watershed, either naturally or due to human activity or infrastructure. So, I will just ask you to recall the hydrological cycle, and we discussed that when hydrological cycle, when water reaches the system atmosphere, then cloud formation occurs, condensation occurs, precipitation occurs, and once precipitation falls, so before reaching the ground surface, it is being intercepted by plants or buildings or any abstract object. So, that is basically from the system perspective, that is a loss, because water is not reaching the surface where it is really utilized, and so on. So, that is how that is what abstraction means, and abstraction can significantly impact the availability and distribution of water resources in a region. So, of course, if the abstraction is more, then runoff will be less. Similarly, another abstraction after reaching the ground surface in hydrological cycle, infiltration occurs. So, from the runoff perspective or surface runoff perspective, that is a loss. So, that means that is how abstractions can impact the availability and distribution of water resources in the region. And of course, once we know abstractions, these help determine surface runoff, subsurface movement and storage of water within the watershed. So, if we know, like just now we said that if we talk about say hydrological cycle, and then there are plants. So, you have cloud formation, taking cloud formation, and then water reaching, precipitation occurring, reaching the surface, and once it reaches the surface, infiltration occurs, and here on the plants interception occurs, and there are others also, but let us talk in terms of only these two. So, when once interception occurs, the total rainfall reaching the ground surface is lowered, and once infiltration occurs, then what is the water available for overland flow, that gets reduced. And so, that is how, if we know the interception, we know the infiltration and other abstractions, then we can find out how much water is available for surface runoff. If we know infiltration, then we know how much water is available for subsurface movement or for storage of water on the surface or below the surface or in the soil. So, this is how important abstractions are. Abstraction could be of different types, just now we talked about. So, this is again a picture of hydrological abstraction in the hydrological cycle. So, we just talked about interception and infiltration with respect to as far as abstractions are concerned. So, interception of precipitation by vegetation above the ground, that is an abstraction, and of course, water gets transpired. So, that is a loss from the system perspective. Evaporation, which occurs from the water body. So, evaporation and transpiration, which combined together we know as evapotranspiration, and that is also an abstraction. And of course, once runoff starts taking place on the surface, then if there are hollows are there on the surface or potholes are there, then water gets stuck into that or gets stored into that, and that is depression storage. And that depression storage on the ground surface due to water accumulating in superficial depressions or hollows, That's also an abstraction, and of course, the infiltration of water into the soil we already saw. So, here you see this particular process was not included earlier in the hydrological cycle, but at that time I said that there are many more processes. So, one such process could be depression storage, which is added here in the hydrological cycle diagram, and that represents an abstraction, depression storage. And of course, out of all these abstractions, the most important one is infiltration. So, that is the most significant abstraction as far as the hydrological cycle is concerned. Now, coming to defining interception, then interception is defined as precipitation water retained on the drainage basin through its adherence to abstract objects such as leaves or other vegetation, buildings, animals, or any such object above the surface of the ground. So, when the precipitation occurs before reaching the ground, if it is retained by any abstract object, could be plant leaves, it could be buildings, it could be animal or say umbrella even, then basically that is nothing but interception. That could be referred to as interception. That is a precipitation, a part of precipitation which does not retain the ground surface and being adheres to abstract objects, maybe it is leaves, maybe vegetation, maybe buildings, maybe animals or any such object, that is interception. Now, interception, of course, out of all these abstract objects, interception by vegetation is most prominent in a hydrological cycle, and that is what our main focus is when we talk about interception. So, interception by vegetation is a function of vegetation type and age, and is expressed as a function of leaf area index. So, I think you know leaf area index, what leaf area index is, and basically this vegetation type and age, that is considered in terms of leaf area index. That is for a particular vegetation type, the age is taken in terms of leaf area index. And of course, it is also function of precipitation intensity, frequency, duration and type. So, of course, it depends on precipitation and of course, the abstract object in this case, which is a vegetation here. So, what happens if you look at this picture, what happens that we have the gross precipitation occurring, and once precipitation occurs, a part of that is intercepted by crown, the canopy of the plantation, and that is referred to as canopy or crown interception loss. So, first thing we come across is canopy or crown interception loss. Then of course, water reaches the ground surface, and there is of course once the water is intercepted, a part of that also falls in the form of through fall, it reaches the surface. But on the if it is a thickly vegetated area or say a forest, then of course you can expect that there will be lot of litters, the tree leaves or branches or portions of the roots, they will be lying on the forest, and so the water, the precipitation before touching the ground or the soil, that will again be intercepted by this litter or forest floor. So, that is referred to as forest floor interception loss. And of course, there will be some part of the water which will drip down through stem reach the surface. So, that is net precipitation. So, from gross precipitation there will be canopy interception loss and there will be forest floor interception loss, and that way we can say that interception, as far as estimation is concerned, the total interception has two components, ET is EC plus EL, and EC is crown interception loss, that is the amount of water intercepted by the crowns of the vegetation, and second one is the forest floor interception loss, EL, which is the amount of water that is intercepted by and evaporated from the forest floor before infiltrating into the soil. So, before infiltrating into the soil, whatever is intercepted and evaporated, that is forest floor interception loss. And there are two more terms which we came across. So, this canopy interception loss is EC we are saying here, and forest floor interception loss we are saying here, we are defining here. There are two other terms which come: through fall, which is the water passing through canopy and reaching the forest floor after dripping from leaves and branches. So, typically if you stand after a rainfall, if you stand below a tree, you will see that lot of water drips through, and that is nothing but through fall. And then is also stem flow, which is here. So, water which trickles along the stems and branches and down to main stem trunk to the ground source. So, from different parts it will reach the main trunk and then it will trickle down to the ground surface, that is referred to as stem flow. So, these are the various components which we typically come across if it is a vegetated area in a say. Now, we can still talk about how to estimate interception, and then crown interception loss is obtained from gross interception, through fall and stem flow, and we can use this relationship. EC is RG minus RT minus RS, where RG is rainfall measured by rain gauges located in nearby openings, RT is rainfall measured by rain gauges under the canopy, and RS is stem flow, which is measured across measured by collars around stem. So, what happens that if you have a forested area or plantation area, then if you put certain rain gauges just below the tree here, that is a rain gauge here, any kind of rain gauge we saw that it could have of different shapes, typically cylindrical, and then we put some of them in open spaces. So, obviously, those who are which are on open spaces, they will not be the rainfall precipitation will not be impacted by intercepts. So, that is RG, and then rainfall will be also collected by the rain gauges which are located below the plantation or below the canopy. Then that simply means that rainfall is reaching the rain gauges after rain is intercepted by the canopy. So, that is why it is called RT, that is the under the canopy. And then what we do in order to find out stem flow, which we say that it is basically the water trickling through the stem and reaching the ground surface. So, if we put some kind of collar here around this stem and we collect that for a significant portion of time, then obviously we can find out how much is. So, net precipitation is stem flow plus through fall, which is basically adding to the ground surface. So, by knowing RG, RT and RS, we can calculate what is the crown interception loss. So, very easy to obtain after experimentation. The next loss is forest floor interception loss. It can be measured by collecting and weighing samples of the forest floor. So, what is done is that we said that there will be litters in the ground which will be trapping the intercepting the rainfall. So, what happens is that if you collect a sample shortly after rainfall, that is when it is soaked by water, and the average loss of weight in the latter samples is interpreted as the amount of intercepted water evaporated. So, if you take a sample immediately or rainfall where a lot of water is there or intercepted water is there, then you let this sample dry and take the weight. So, the difference in the weight will be only because the water that has evaporated or that was intercepted by forest floor. So, that is referred to as forest floor interception loss. Typically, interception accounts for 3 to 5% of the total precipitation. That also in typically in a normal circumstances, and that is why, because it only accounts for 3 to 5%. Many a times in hydrological modeling, when we take a comprehensive model, this portion may be neglected, or it is many a times it is neglected actually because of this small magnitude, but there are many other models which take this interception loss into account while modeling or calculating the entire water balance equation. Now, coming to staying into the estimation of interception. So, besides experimentation, there are certain mathematical models also available for estimating interception, and one such model is given by Jensen, which was given in 1983. So, Jensen model 1983 can be used, which was developed mainly for agricultural crops, and as per this model, size of maximum storage capacity, which is nothing but the interception, the maximum interception I max is C int into LAI. So, basically here C int is the interception parameter in millimeters, and LAI is the leaf area index of the crop or the vegetation. It is an agriculture crop. So, it is a agriculture crop, that is why we are defining in terms of crop, but it can be also used for plants also. And typically the value of C int, the interception parameter, is taken as 0.05 for agricultural crops. Thus, interception is taken as a function of vegetation type and stage of development through leaf area index, which we also mentioned earlier. So, let us take an example, and that says that for V1 red rice, this is the vertical name Condor Dano, the leaf area index and the interception parameter for different seasons are given in the table. So, it is a LAI and C int. So, basically 30 days DAS here is days after sowing. So, 30 days after sowing, 45 days after sowing, 60 days, 75 days and 90 days, the values of LAI and C int are available. Find the total maximum storage capacity of the crop in the entire season. What is the percent increment in the total maximum storage capacity between 45 DAS and 90 DAS? So, obviously, we know that Jensen model I max is C int LAI, and because we have the C int values and LAI varies. So, we can calculate the I max or the maximum interception after 30, 45, 60, 75 and 90 days, and these are the values, and total comes out to be 0.496. That simply means the total maximum storage capacity of the crop during the entire season is 0.496 millimeters. Total maximum interception capacity is 0.496 millimeters. And the second bit was that what is the percent change in 45 DAS and 90 DAS. So, after 45 DAS, the total maximum storage capacity will be sum of these two. So, it is 1.117 mm, and of course, 90 days, that is the end of the season, we know already sum, it is 4.496 mm. So, the percent change, the total maximum storage capacity between 45 and 90 days is 0.496 minus 0.117 divided by 0.117, and it comes up with 324%. So, that means between 45 days and 90 days, the maximum storage capacity goes up by 324%, and that is primarily because of the value of the leaf area index. The leaf area index is changing drastically over the period of time. Then we have also the Horton model, and Horton model came into existence in 1919, and as per Horton model, interception loss equals the combined losses from intercepted water during precipitation event and intercepted water in canopy storage. So, these are the two different components here, and the total volume of water intercepted can be calculated by this formula, or this is the model. Li is S plus K E T, where S is the interception storage, K is the ratio of surface area of the leaves to the area of the entire canopy, very similar to LAI, but defined in a different way. E is the rate of evaporation during the precipitation event, and T is the duration of the precipitation. So, Horton equation suggests that the total interception is dependent on the storm duration. As longer duration storms allow more evaporation from the canopy during the storm event. So, obviously, if T value is high, then obviously, because T here is the duration of precipitation, so if T value is high, Li will be high. And interception varies widely by seasons because of a simple reason. Say, for example, the deciduous trees, if you consider, they will lose much of their canopy storage potential during the winter months. So, in winter months, if we have a plantation of deciduous trees, then obviously the interception loss will be very, very less, because this part K will be very, very low in that case. Then we have another model given by Marian, which is called Merriam model 1960, an exponential equation that considers diminished interception storage with increasing precipitation. So, this is the form. So, here it is says that the interception decreases exponentially, and I is the interception loss, S is the interception storage, the interception storage reduces, P is the gross precipitation here, and E is the rate of evaporation during the precipitation event, and T is the duration of precipitation. So, just a modification of the Horton model, which is given in the exponential form. That was more into linear terms, and then this is more exponential. Then we come to the next part, abstraction, which is depression storage. Now, we already saw defined depression storage. Depression storage or ponding is that water on the drainage basin that drains into closed depressions and never reaches the outlet of the basin. So, if you remember the hydrological cycle equation picture just now, we saw that when rainfall occurs, interception occurs in form of infiltration, then surface runoff or overland flow starts taking place. Now, once the flow is taking place on the surface, if it comes across a depression or hollow or pothole on the surface, then obviously the water will be stuck there, and of course, runoff will take place after filling that pot. The water will continue to flow, but whatever water that is retained in the pot, that will not be a part of the water reaching the outlet. So, this will never reach the outlet, and it will be there in the closed depressions. This water remains trapped in depressions. Some eventually evaporates and remainder infiltrates into ground. So, it does not become a part of the surface runoff, but it infiltrates. It has to obviously get lost. So, a part of that infiltrates and a part of that gets evaporated. Now, coming to estimation of depression storage, we have two different ways of doing that. The first one is using hydrological budget, and if we write a water balance equation in terms of depression storage, then it comes out to be rainfall minus runoff minus infiltration minus evaporation minus interception. So, of course, during our discussion, water balance equation will be seen in different terms many times. So, here we are looking at in terms of depression storage. So, these are the various other variables involved in the hydrological cycle. So, if we have the values of rainfall, runoff, infiltration, evaporation and interception, then we can estimate depression storage. And out of these, rainfall, evaporation and runoff, they can be measured, and infiltration and interception can be estimated, and thus we can find out the depression storage. So, this is one way of estimating depression storage, that is by using the hydrological budget equation. The other way is using the models of superficial depression, that is, say, one such model is given by Lindsley in 1949, where the amount of water stored in a given time by superficial depression is given by this equation, V equals to SD 1 minus exponential minus KPE, where V is the amount of water stored at time t, SD is the maximum depression storage capacity, PE is the precipitation excess, that is gross precipitation minus evaporation minus interception minus infiltration at any time t, and K is a constant which is also expressed in terms of SD, which is the maximum depression storage capacity. So, if we know the variables, we can calculate the amount of water stored in that superficial depression, or we can estimate the depression storage. Now, value of SD, I mean the most important variable is from the surface point of view is SD, and of course, this is the maximum capacity. It is defined as the maximum depression storage capacity. So, that means we have to find out the size and shape of storage, and it can be obtained from topographic maps or field measurements. So, if you have a contour map at finer scale, or even if you can go and find out, measure the potholes, then we can find out what is the maximum storage capacity of these depressions. Now, if P is very large, that is the effective rainfall is very large, then V approaches the value of SD. That means the depression storage will be fully filling the SD. That means it will be fully. If P is negligible, then B will also be negligible. That means depression storage can lie between 0 and SD, where SD is the maximum depression storage capacity, which we can find from topographic maps or by field measurements. Now, we have an example. A 3.5 hour storm deposits 25 millimeter of rainfall over a catchment area of 12 hectares. Catchment has 30% of its area covered by vegetation and 25.5% of area is under depression. Depth of total interception during the storm is 8 mm and total maximum depression storage depth from the field measurement is 10 mm. The fine index during the storm is 5.5 millimeter per hour and infiltration occurs over 40% of the catchment area. Evaporation is 10% of maximum depression storage. Find the volume of water stored by superficial depression during the storm, and of course, we can use the formula just now we discussed, that is Lensley and others 19 equation. Now, for determining SD, we have been given total catchment area and we have also been given maximum storage depth, which comes out to be 10 mm. Total depression area is defined as 25% of the catchment area. That means 25.5% of the 12 hectares will be the total depression area, which is in square meters 3.06 into 10 power 4. So, maximum depression storage capacity can be found out by multiplying these two numbers, and that comes to be 306 cubic meter. And thus, constant K of Lensley equation, which is 1 by SD, is 1 by 306. Now, effective rainfall, gross precipitation is given as 25 mm. Volume of gross rainfall can be obtained by multiplying it with the area of the catchment, and total vegetation area is given as 30.5% of the catchment area. So, total vegetation area also we can calculate. The total depth of interception is 8 millimeters. So, we can volume of interception during storm we can calculate by considering the total basin. Similarly, phi index is given, storm duration is given. So, total infiltration area is also given, 40% of catchment. So, total infiltration volume we can calculate. Similarly, total evaporation volume is also given, it is 10% of SD. We have already calculated SD, so we know 3.06. Now, precipitation exercise is Pg minus E minus V infiltration by I. So, putting these values we get 1780.14, and now we know Pe, we know K, we know SD. So, putting in this equation we can calculate V, that is volume of water stored by superficial depression, which comes out to be 305.08 cubic meters for the given data. So, that is basically we are using the Lensley equation and also total water balance for finding out the precipitation excess actually. Now, coming to evaporation. Evaporation is the process whereby liquid water is converted to water vapor by transfer of water molecules to the atmosphere. So, basically because of the heat as well as the vapor pressure changes, this evaporation takes place. And it is small during the rainfall runoff event and can be neglected, and bulk of this abstraction takes place during the time between runoff events, which is usually long, and hence evaporation is more significant during the time interval. So, basically during when the rainfall is occurring, because vapor our air will be saturated, so there is very little evaporation taking place, but between two rainfall events this evaporation loss will be very high and it becomes significant. So, that is why we may have event model and continuous model. If you consider in a event model, we may neglect evaporation, but evaporation is very important for a continuous model, kind of hydrological model. Coming to factors affecting evaporation rate, of course, the vapor pressure at the water surface and the air above the water surface, that is the most significant factor, and basically it follows Dalton's law of evaporation, where EL is C, EW is minus E, that is the rate of evaporation is proportional to the difference between saturation vapor pressure EW at the water temperature and the actual vapor pressure in the air. And obviously, if the difference is large, the evaporation will be more, and evaporation will occur as long as EW is greater than EA. So, when EW becomes equal to EA, then there will be no evaporation. Wind speed. Winds help in removing the evaporated water vapor from zone of evaporation. So, rate of evaporation increases with increase in wind velocity up to some limit. So, critical wind speed. So, up to certain level, if wind speed is high, the evaporation will be high. Considering air and water temperature, obviously we can expect that the rate of evaporation increases with the increase in water temperature and air temperature, and water temperature is highly correlated to evaporation rate. Then size of the water body. Large water bodies have high evaporation due to high wind speeds, also because of their size. Atmospheric pressure. Decrease in atmospheric pressure as we experience in high altitude areas increases the evaporation rate. And as far as soluble salts are concerned, when a solute is dissolved in water, vapor pressure of solution is less than that of the pure water, hence the rate of evaporation reduces. Consequently, evaporation from saline water bodies like a sea and ocean is 2 to 3% less than the freshwater bodies. So, this is evaporation and the factors affecting evaporation. In the next lecture, we will talk more about evaporation. So, today in this lecture, we talked about abstraction in the form of interception and depression storage. We started with evaporation and we will continue the discussion. Please feel free to give your feedback and also raise your doubts or questions which can be answered in the forum. Thank you very much.